A clock ticks. Its hands sweep across a circle of numbers, measuring seconds as if they were beads on a string. We trust that ticking. We build our lives on it. Every breath, every sunrise, every orbit of the Earth around the Sun seems to prove that time flows, steady and unyielding. Look up on a clear night. Between the stars yawns a vast emptiness we call space. We imagine it as a stage, cold, silent, eternal, where galaxies drift like scattered lanterns, while time is the invisible current carrying them forward. For centuries, this vision felt secure. The world's events unfolded on a grand, unchanging backdrop. But what if that stage is not real? What if the ticking of the clock, the distance to the stars, even the sense of before and after, are not fundamental at all, only convenient illusions, born from the way we perceive the universe? This is the paradox that modern physics has forced upon us. It begins like a crack in the mirror of certainty. Everything we think of as basic, distance, duration, direction, may be secondary, not primary. The universe might not exist in space and time. Instead, space and time themselves may emerge from something deeper, something we can barely describe. Centuries ago, Isaac Newton declared that space and time were absolute, vast containers that existed independently of the things within them. The apple fell toward the ground because forces acted within that container, and the ticking of a clock simply revealed the universal river of time that flowed everywhere at once. It was a comforting picture. The cosmos was a grand stage, and all the drama of planets and stars unfolded upon it. Then came Albert Einstein, who shattered that certainty. His theory of relativity showed that time and space were not rigid frames but flexible, intertwined dimensions, space-time, that could stretch, twist, and ripple. Gravity was no longer a mysterious force acting across empty space. It was the curvature of space-time itself. The ticking of the clock slowed near a massive star. The distance between 2 points changed as the universe expanded. The stage had become part of the play. For a while, this new vision seemed complete. Einstein's equations explained the motion of planets, the bending of starlight, even the birth of the universe in a hot, dense Big Bang. But as scientists peered deeper into the subatomic world governed by quantum mechanics, cracks appeared again. At the tiniest scales, where space-time itself ought to be smooth and continuous, it behaved like a stormy sea, fluctuating wildly. The neat geometry of Einstein's cosmos began to dissolve into quantum foam. If the universe's fundamental laws arise not in a pre-existing space and time, but in a kind of deeper, pre-geometric reality, then the very notion of before the Big Bang might be meaningless. The beginning we imagine, a singular point from which time erupted, may have been no more than a change in the way reality organizes itself. Think of it this way. A mirage on a hot road looks like water, but it is only light bending in heated air. Space and time may be mirages of a similar kind. Convincing because they are all we have ever known, but not truly fundamental. Pause and picture that. The solid sense of here and there, the ceaseless march of then into now. What if these are not pillars of the cosmos, but patterns our minds have evolved to track the unfolding of events? It is as if the universe were a storybook whose pages have no fixed grid, yet we draw lines across them to keep track of where we are. Some physicists now explore theories where space itself arises from networks of quantum entanglement, threads of correlation that do not sit in space but give rise to it. Others propose that time may be an emergent property of change, not a flowing river, but an illusion born from the ordering of events. In such pictures, the familiar four-dimensional arena of space-time is like the surface of a lake, calm and continuous from far away, yet underneath made of countless invisible drops. This idea unsettles us because it strikes at our deepest intuitions. A clock on the wall feels more real than any particle, more reliable than any equation. But those ticking seconds may be as deceptive as the horizon that once fooled sailors into believing the Earth had an edge. The closer we sail toward that horizon, the more it retreats. Imagine the cosmic clock we have trusted for so long. The great pendulum of time swinging from the Big Bang onward. Now picture that pendulum shattering, its fragments scattering like glass. Without the framework of time, what becomes of cause and effect? Without the scaffolding of space, what becomes of where we are? The question is not merely academic. If space and time are emergent, they could break down in extreme conditions, near black hole singularities, in the first instant of the universe, or perhaps at the ultimate edge of physical law. In those realms, the equations of Einstein's relativity falter, and the language of before and after no longer applies. It is tempting to recoil, to cling to the comfort of the familiar stage. But history teaches us that every time we thought we had found the ultimate foundation, it dissolved beneath us. The Earth was not the center of the cosmos. The sun was not fixed among eternal stars. Space-time itself may not be the bedrock, but another layer of the illusion. The paradox is as liberating as it is unsettling. If the stage is fragile, then the drama may be deeper and more surprising than we imagined. We may be like actors discovering that the theater's floor and walls are themselves part of the performance, that the play is still being written at levels of reality we can scarcely conceive. Consider the distance to the farthest galaxies, billions of light years away. We picture them sitting in remote corners of space, their ancient light trudging across an empty void. But if space is emergent, then that void is not a passive corridor. It is part of the same mysterious fabric that links all. Things, what we call far away, might be no more fundamental than the lines of longitude and latitude on a map, useful for navigation, but not ultimate. And the ticking of a clock? Perhaps it is the sound of change echoing through a pattern that has no true flow, no universal tempo, only local rhythms created by interactions of energy and matter. What we experience as time's passage may be the way our minds stitch events together, like frames in a film. By the end of this journey, you may never look at the empty night sky the same way again. Darkness between the stars is not simply nothing. It may be the veil of a deeper order whose contours we are only beginning to glimpse. We began with a simple question. What is more real than the clock's tick, or the stretch of the void? We end this opening chapter with a more unsettling one. If the stage on which the universe unfolds is itself an illusion, what does that say about the origin of the play? And about the role we, the fleeting actors, truly occupy? We once imagined the universe as a grand, unchanging hall. Its walls were the infinite expanse of space. Its clock was an invisible metronome, ticking the same beat everywhere, from the hearts of stars to the heartbeats of men. That vision, simple and reassuring, was the world according to Isaac Newton. Newton's cosmos was a stage, vast, rigid, eternal. On that stage, planets traced their ellipses, apples fell from trees, comets swept across the sky. Nothing in the play could alter the stage itself. Space and time were containers. They did not bend or ripple. They were the fixed arena in which all motion took place. Gravity, in this view, was a mysterious force acting across empty distance, an invisible tug that bound Earth to the sun and the moon to Earth. For more than 2 centuries, this picture ruled our understanding of nature. It made the heavens calculable, turned falling apples into equations, and allowed us to predict eclipses centuries in advance. The universe seemed orderly, rational, and absolute. Time's flow was the same for all, the pulse of eternity. Space was the same everywhere, a perfectly still stage on which the cosmic drama unfolded. Yet, even as Newton's vision reigned, hints of its fragility appeared. The speed of light, first measured with painstaking care in the 19th century, seemed constant no matter how fast the source or observer moved. No etheric wind carried it. No matter how you chased it, it remained out of reach. That constancy clashed with the simple arithmetic of velocities that Newton's mechanics assumed. It was the first faint ripple in the rigid. Enter Albert Einstein in 1905. In his special theory of relativity, he took that stubborn constancy of light seriously. The result was revolutionary. Time and space themselves could no longer be absolute. The faster you moved, the slower your clock ticked, compared to someone at rest. Distances contracted for you as you approached light speed, events that seemed simultaneous. To one observer unfolded in sequence to another. Time and space were not universal rivers and scaffolds. They were threads woven together, stretching and compressing in response to motion. A decade later, Einstein took the next audacious step. In his general theory of relativity, he revealed that gravity was not a force at all, at least not in the Newtonian sense. What we feel as gravity is the bending of space-time itself, the very stage on which everything moves. Planet does not orbit the sun because some invisible tether pulls it. It follows the straightest possible path, a geodesic, through a curved space-time shaped by the sun's mass. This insight turned the universe inside out. The stage was no longer fixed. It was dynamic. Mass told space-time how to curve, and curved space-time told mass how to move. The familiar grid of rulers and clocks dissolved into a supple, interactive fabric. Imagine that fabric as a taut sheet stretched in the dark. Place a heavy sphere on it. The sheet dips. Roll a marble nearby, and it spirals inward. Not because the larger sphere reaches out and pulls it, but because the fabric itself guides its path. This picture, simplified but evocative, replaced Newton's distant tug with local geometry, and the consequences went far beyond orbiting planets. If space-time could bend, it could ripple. If it could ripple, it could collapse. Einstein's equations predicted black holes, regions where the fabric folds so steeply inward that not even light can climb out. At the center of such a hole, all known physics breaks down. Space-time itself seems to end in a singularity. Black holes turned out not to be exotic curiosities but common denizens of the cosmos. Massive. Stars die in implosions that puncture space-time. At the hearts of galaxies, including our own, lurk supermassive black holes millions to billions of times heavier than the Sun, shaping the growth of galaxies themselves. Here was the first great cliffhanger. Relativity revealed that the stage is pliable, even fragile, but it left unanswered what the fabric is actually made of. It could describe its curvature, but not its essence. Relativity also shattered the notion of a universal clock. The flow of time became local. Near a massive body, time ticks more slowly. A clock on the surface of the Earth runs infinitesimally slower than one on a mountaintop. Astronauts circling Earth age a fraction of a second less than those they left behind. In the warped space-time near a black hole, time can stretch so dramatically that a few hours for one observer may equal years for another. This raises an unsettling paradox. If time itself can stretch and contract, is it really flowing at all? Or is it merely the way we experience the sequence of events in a geometry that itself is malleable? Einstein's theory provided an exquisitely accurate description of how space-time behaves. It predicts the bending of starlight during eclipses, the expansion of the universe, the dance of binary pulsars, the existence of gravitational waves that we have now detected, but it did not answer what space-time is. Is it a substance, like an invisible fluid pervading the universe? Or is it a set of relationships, a mathematical bookkeeping of how matter interacts? This question echoes like a riddle beneath the triumph of relativity. Philosophers have long wrestled with the same puzzle. In Newton's time, the debate was between absolutists, who saw space and time as entities in their own right, and relationalists, who saw them as nothing more than the distances and durations between events. Einstein seemed to vindicate the relational view. Space-time was dynamic, inseparable from the matter within it. Yet his field equations treat space-time almost as if it were an elastic medium with its own energy and dynamics, hinting at a kind of physicality. The tension deepens near the edges of Einstein's theory, in the heart of black holes and the first moments after the Big Bang. There, the smooth fabric wrinkles into something unrecognizable. We need a theory of quantum gravity, a deeper framework where space-time itself is not fundamental but emergent, arising from more basic constituents. Perhaps networks of entanglement, perhaps something stranger still. Relativity was a grand leap, but it left us staring into an abyss of questions. We can describe how space-time curves, yet not why it exists. We can trace the trajectories of planets and photons, yet not the genesis of the arena they travel through. Consider again the taut sheet analogy. We understand how a ball makes the sheet sag, But what is the sheet itself? What gives it its tension? What happens if we zoom in so closely that the notion of a smooth sheet breaks apart into some deeper microscopic structure? This is more than idle speculation. Einstein's theory, magnificent though it is, cannot be the final word. Quantum physics governs the very small, and when we try to stitch it together with general relativity in extreme conditions, contradictions arise. The equations predict infinities where there should be finite answers. We glimpse, through those inconsistencies, that space-time as we know it may be a macroscopic approximation, a surface layer of a deeper reality. For now, though, Einstein's fabric remains our best map of the cosmic terrain. It has guided our probes past the giant planets, steered our spacecraft with uncanny precision, allowed us to detect the whisper of colliding black holes from billions of light years away. It lets us predict the slow spiral of stars around galactic centers and the bending of light from distant galaxies into cosmic lenses. Yet even as we celebrate its power, we must confront its limits. At the core of every black hole lies a singularity where the curvature of space-time becomes infinite, an unmistakable sign that our map has reached its edge, and if the universe itself began in a hot, dense state, then the moment of its birth was also such a singularity, one that relativity cannot describe. The fabric that replaced Newton's stage thus proves not to be the ultimate stage, but a temporary set. Astonishingly effective for most of the play, yet destined to fail in the most extreme acts. This realization leads to another cliffhanger. If the stage is not ultimate, or titoi fortweit, then what deeper principle writes its script? What hidden architecture underlies the geometry we call space-time? Einstein showed us how the stage can bend, but he could not tell us what the stage is. The journey from Newton to Einstein was not just a shift in equations. It was a shift in metaphysics. We ceased to think of the universe as an event, playing out inside a pre-existing container. We learned that the container is part of the event. In this insight lies both the triumph and the unfinished business of modern physics. The story of gravity itself reflects this transformation. For Newton, gravity was an inexplicable action at a distance, a mutual tugging across empty void. For Einstein, it is the manifestation of geometry, the natural path objects follow when space-time is curved. The mystery of why masses attract became the puzzle of why space-time bends, and what bending truly means. Look at a photograph of gravitational lensing, the light of a distant galaxy stretched into an arc by the warped space-time. Around a massive cluster, you are seeing not merely a visual trick but a fingerprint of geometry itself, a direct sign that the stage is pliable and active. Think of the first detection of gravitational waves in 2015, two black holes spiraling together a billion years ago, shaking the very fabric of space-time, sending out ripples that stretched and squeezed every ruler on Earth as they passed. We heard, for the first time, the ringing of the cosmic fabric. It was as if the universe itself had a voice, carried not by sound, but by the oscillations of the arena in which all motion occurs. Each of these discoveries deepens the wonder, but also sharpens the paradox. If the stage can bend, ripple, and even tear, it begins to feel less like an abstract geometry and more like a physical entity. Yet we still do not know what kind of entity it is, or whether that sense of substance is itself a mirage. We stand, then, at a precipice in understanding. Behind us lies Newton's solid hall of space and universal time, a comforting illusion now dissolved. Beneath our feet stretches Einstein's supple fabric, predictive, elegant, yet incomplete. Ahead lies an uncharted realm where the very notions of space and time may arise from something even more fundamental. At every conceptual leap, from Newton's stage to Einstein's fabric, from fabric to its quantum underpinnings, the questions only deepen. We peel away one layer of the cosmic illusion to find another beneath it, each revealing a universe stranger than the last. And so we close this chapter with a lingering puzzle. Relativity has brought us closer than ever to understanding the play of gravity and motion. Yet it has not told us what the stage is made of. We have seen that space and time are not the passive backdrop we once imagined, but the dynamic participants in the cosmic dance. But if they themselves are dancers, not the floor beneath the dance, then what lies deeper still, waiting to be revealed in the next act of our quest? Imagine peeling back the layers of the universe as if it were a vast, luminous tapestry with each layer removed. The weave grows finer. Galaxies give way to stars, stars to planets, planets to atoms, atoms to quarks. You keep zooming in, convinced that somewhere there will be a final thread, the ultimate strand of the cosmic fabric. But keep going, far beyond anything you have ever seen. Past the scale of protons, past the heart of quarks themselves, at a length of about 10 to the power of minus 35 meters, the Caudy Planck length, the very notion of a smooth thread unravels. The fabric you thought you were approaching shivers and blurs. It no longer looks like fabric at all. At this scale, space-time itself, the stage that Einstein gave us, ceases to behave as a continuous sheet. It froths and foams like the surface of a storm-tossed sea. Tiny bubbles of geometry blink into existence and vanish almost instantly. Distances and durations lose their usual meaning. To ask where or when something is like asking the crest of a wave in a hurricane to hold still and be measured. This is the domain of the Planck time, around 10 to the power of minus 43 seconds. Below this unimaginably short span, even the sequence of before and after begins to dissolve. Causality, the bedrock of common sense, becomes a tenuous concept. Through the steady river of time, we thought we knew fragments, into eddies and whirlpools, sometimes looping back on itself, sometimes seeming to evaporate. Here lies the first great rebellion. Quantum physics refuses to accept the smooth continuum that general relativity assumes. Einstein's elegant geometry works splendidly on large scales. Stars, galaxies, the expansion of the universe. But when we try to shrink it down to describe the realm of the very small, it collapses into contradictions. Its equations blow up to infinity, like trying to calculate the curvature of a coastline drawn in jagged lightning strikes. Quantum mechanics, by contrast, is built on probabilities and uncertainty. It says that particles do not have definite positions and velocities until they are observed. They exist in a haze of potentialities. Space itself, in this view, cannot be infinitely divisible. It must have some kind of granular, fluctuating character, or the mathematics refuses to make sense. At the smallest scales, the serene arena of relativity turns into a foaming chaos. It is as though we have been trying to fit a fluid theory of water into a world that, under a powerful enough microscope, is revealed to be a dance of discrete molecules. Relativity gives us the flow. Quantum theory demands that we reckon with the discrete dance. The clash between the two is not merely a technical nuisance. It tells us that space-time, so fundamental to one theory, cannot be fundamental to the other. Some deeper layer of reality must exist beneath both. Something that produces space-time as an emergent pattern, the way a grid of pixels can produce the illusion of a smooth image on a screen. This is why many physicists now speak of space-time as if it were not the ultimate stage, but a secondary phenomenon, a large-scale appearance of something more elemental. The question is, what? Some researchers have pursued a vision called loop quantum gravity. In this approach, space-time is not continuous but woven from tiny loops of quantized geometry, like a lattice of interlinked rings. Distances and areas in such a world come in discrete chunks, indivisible units set by the Planck scale. The smooth curves of Einstein's equations emerge only when these loops are seen from far enough away, much as a woven fabric looks smooth to the naked eye, but reveals its threads under a microscope. In loop quantum gravity, space is granular, and time may be nothing more than the ordering of changes in these quantum loops. It is an enticing picture, one that suggests that the Big Bang singularity might be replaced by a bounce, a prior phase of the universe collapsing and then rebounding, never reaching infinite density because the granularity of space resists further compression. Yet this vision is not universally accepted. Others seek a deeper unification in string theory, which replaces point-like particles with tiny vibrating filaments of energy. In string theory, the familiar 4 dimensions of space-time are joined by extra hidden dimensions, curled up so tightly that we cannot see them. The vibrational modes of the strings give rise to all the particles and forces we know. Gravity itself emerges naturally from certain modes, hinting that the fabric of space-time is not fundamental but derivative, a consequence of the deeper dynamics of strings. String theory has spawned an even more radical idea, the holographic principle. According to this principle, the information needed to describe everything within a volume of space can be encoded on its boundary, much as a hologram on a 2-dimensional surface can project a 3-dimensional image. If true, then our 3-dimensional world, and perhaps even time, could be a kind of projection from a more fundamental reality living on a distant boundary. These concepts may sound abstract, but they arise from concrete puzzles. Black holes, for instance, possess a curious property. Their entropy, a measure of the information they contain, is proportional not to their volume, but to the area of their event horizon. This strange scaling suggests that the ultimate degrees of freedom of space-time itself reside not in the bulk of the universe, but on its surfaces. From this insight has grown a Vision of the universe where the smooth space-time we inhabit is like the surface of an ocean, while the true microscopic degrees of freedom, the molecules of space-time, lie hidden beneath, or perhaps on, a distant edge. In some formulations, our cosmos might be comparable to a vast, dynamic hologram. Pause and let the implication sink in. The distances we measure, the flow of time we feel, might be akin to the vivid scenery in a virtual reality. Real enough for our purposes, yet not fundamental. If so, the ultimate description of reality might be written not in the language of geometry, but in the language of information and quantum entanglement. Entanglement, that eerie link between particles that defies classical separation, has emerged as a surprising hero in this story. Some researchers argue that the fabric of space-time itself is woven from entanglement, that the connectivity of space arises from the pattern of quantum correlations among deeper degrees of freedom. If the entanglement is severed, the spatial link dissolves. This picture inverts our intuition. We tend to think that particles become entangled because they share a location in space, but perhaps they share a location in space because they are entangled. In that case, space is not the container but the consequence, a byproduct of underlying quantum relationships. To stand before this idea is to feel both awe and vertigo. T-108 suggests that the ultimate essence of reality may not be stuff or even geometry, but relations, patterns of information and correlation that, when viewed collectively, give rise to the experience of being somewhere at some time. Yet the rebellion does not end here. Even if space can be described this way, time remains an especially stubborn mystery. Quantum mechanics treats time as an external parameter, a stage upon which wave functions evolve. Relativity, by contrast, fuses time with space into a single dynamic entity. A full quantum theory of gravity must somehow reconcile these views, or perhaps replace them with something more radical, a world without time as we know it. Some speculative approaches hint that time may emerge from entanglement as well, from the way correlations grow or change. Others see time as a measure of the increase of entropy, a bookkeeping of change rather than a fundamental dimension. In any of these pictures, the relentless forward march of time that we feel in our lives would be a large-scale illusion, much like the smoothness of a beach that up close is only shifting grains of sand. The implications ripple outward into philosophy. If space and time are not fundamental, then causality itself, the chain of causes and effects that underpins our reasoning, may be emergent too. The very grammar of reality could be secondary, arising from deeper rules we have not yet glimpsed. Picture again the cosmic fabric. Einstein taught us to see it as a continuous sheet that can bend and ripple. Quantum theory suggests that if we zoom in far enough, the sheet unravels into bubbles and loops, into something like a digital code. Bits of information flipping, networks linking and unlinking. Beyond that lies a question still more profound. What principle animates those bits? What breathes existence into the code itself? This is the second great cliffhanger of our quest. Relativity gave us a stage that could curve. Quantum mechanics whispers that there is no stage at all, only a flickering pattern from which the illusion of a stage arises. The challenge of uniting the two is not merely to adjust equations, but to rethink what it means for something to exist. In our daily world, meters and seconds feel as solid as bricks and steel. But the quantum rebellion reveals that they may be conveniences, approximations that hold only because we never look too closely. Like the apparent smoothness of a photograph that is, upon magnification, an array of discrete pixels, the continuity of space-time may be the artifact of limited resolution. The Planck scale marks the boundary of that resolution. Below it, our familiar measurements dissolve. Concepts such as distance, duration, even direction become fuzzy. It is as if reality itself refuses to be probed beyond a certain point, guarding its ultimate code from our instruments. This threshold raises a final, unsettling possibility. If space-time is emergent, then the Big Bang may not have been the origin of everything, but merely the moment when this emergent phase crystallized, the way liquid water can condense out of vapor. There may have been a deeper pre-space-time epoch, one we cannot yet describe, where the notions of here and there, before and after, had no meaning. Such reflections are not idle fantasies. They shape how physicists build new theories, how they interpret data from black holes, from cosmic microwave background radiation, from particle accelerators, and they remind us that our familiar picture of a universe laid out in space, evolving in time, is at best provisional. As we gaze into this abyss, we are forced to confront a humbling truth. The most familiar features of our world may be illusions born of scale and perspective. The clock's tick and the ruler's stretch may be like the sound and sight of waves, real phenomena, but not the fundamental elements of the ocean. The quantum rebellion thus invites not only new mathematics, but new imagination. We must be willing to picture reality as a web of correlations, a fluctuating foam, a tapestry woven from the invisible threads of information. We must also be ready to accept that even such pictures are metaphors, temporary scaffolds on the way to deeper understanding. At this juncture, science and philosophy meet. The question of what space and time ultimately are is also the question of what it means for anything to exist at all. We are drawn to ask whether the universe is a physical object, a mathematical structure, a network of relationships, or something that transcends all these categories. Whatever the answer, one lesson is already clear. The stage on which we thought the cosmic play was performed is not the immutable foundation we imagined. It is more like the shimmering image on a screen, responsive, dynamic, perhaps even ephemeral. In pursuing its secrets to the smallest scales, we discover not solidity, but a strange, almost digital undercurrent. And as we stand at the threshold of this deeper understanding, we find that our oldest intuitions of space as an endless expanse and time as an unbroken river have betrayed us. The universe at its roots is stranger than the dreams of our ancestors, stranger even than the equations of our greatest physicists so far. Its essence may be neither matter nor geometry, but the subtle play of possibility itself. We began this chapter seeking the nature of the fabric. We end it with the realization that the fabric might be no more than a pattern projected by a more fundamental loom, a loom whose threads we are only beginning to glimpse, the rebellion of the quantum realm is not just a challenge to old theories. It is a summons to reimagine reality from the ground up. Imagine holding a thin, transparent film in your hand. Shine a laser through it, and suddenly a three-dimensional image blooms into view, floating in the air. The image looks real enough to reach out and touch, yet you know it is a projection. The information that defines it resides entirely in the two-dimensional surface of the film. Now imagine that the entire three-dimensional universe you inhabit, the stars above you, the chair beneath you, the sense of here and there, might be like that holographic image. All the information describing it could be stored on a distant two-dimensional boundary, perhaps the far-flung cosmic horizon itself. The depth you experience would be real to you, yet not fundamental. This is the unsettling possibility raised by modern physics. It did not arise from idle speculation, but from a hard-won confrontation with one of nature's most extreme laboratories, the black hole. In the early 1970s, Jacob Bekenstein noticed something peculiar about black holes. If you dropped matter carrying entropy, that measure of disorder and information, into a black hole, you seemed to violate the second law of thermodynamics. The total entropy of the universe should not decrease, yet the black hole seemed to swallow it without trace. To resolve the paradox, Bekenstein proposed that black holes themselves possess entropy, a kind of hidden information content, proportional not to their volume, as one might expect, but to the area of their event horizon. Stephen Hawking deepened this insight when he showed that black holes are not entirely black, but emit a faint thermal glow, now called Hawking radiation, as if they have a temperature. A black hole can evaporate, leaking energy until it disappears. Its entropy, too, seems tied to the area of its surface. This was the first cliffhanger. Why should the ultimate repository of information in the universe scale with surface area rather than with volume? We live in a three-dimensional world. Surely the number of distinct configurations in a region ought to grow with the region's size. Yet black holes tell us that nature counts information by surface area, as though the true bookkeeping of reality resides on boundaries. From this strange clue emerged the holographic principle, formulated most famously by Gerard 't Hooft and Leonard Susskind. It states, in essence, that the maximum amount of information that can be contained within a region of space is proportional not to its volume, but to the area of its boundary. All that happens within could, in principle, be encoded on that surrounding surface, much like a holographic plate encodes a 3D scene. Pause and let the implication sink in. If the holographic principle is correct, then the universe's fundamental degrees of freedom may live not in the space we see, but on a distant boundary, with the bulk of space arising as a projection, a grand illusion, woven by the pattern of that boundary's data. This idea found striking mathematical expression in the late 1990s through the work of Juan Maldacena. He discovered a remarkable duality between two very different kinds of theories. A gravity-based theory defined in a bulk region of space that includes time. In this case, a universe with negative curvature, called anti-de Sitter space, and a quantum field theory defined on the lower dimensional boundary of that region. This correspondence, known as Adase's CFT duality, gave physicists their first concrete realization of the holographic principle. Everything that happens in the higher dimensional, gravitational world can be described by a theory, without gravity living on the lower dimensional boundary. While our own universe is not anti-de Sitter in shape, it appears to be more like a de Sitter, space with positive curvature. The duality suggests something profound. Gravity and the geometry of space itself might be emergent phenomena, arising from the dynamics of more fundamental degrees of freedom on a lower dimensional surface. This realization reshapes the very notion of location. We are used to thinking that where we are is a fact about position in three-dimensional space. But if the 3D space itself is a kind of projection, then here is defined not by intrinsic coordinates, but by the structure of information on a deeper level. The holographic view suggests that the cosmic stage we see is like the vivid moving picture on a screen, while the true data, the script, lies encoded on the screen's surface. To ask what is over there versus over here is, in some sense, to ask about correlations in that hidden two-dimensional ledger. It is a dizzying reversal of perspective. We used to imagine ourselves living inside a giant container called space. Now, it appears that the container itself may be the emergent appearance of something more. Abstract entanglement plays a starring role in this picture. In recent years, researchers have discovered deep links between the pattern of quantum entanglement in the boundary theory and the shape of the bulk geometry. A celebrated proposal by Mark van Ramsdonk suggests that if you reduce entanglement between parts of the boundary, the corresponding regions of the bulk universe begin to drift apart, as though spatial connectivity itself arises from the web of quantum correlations. In the extreme limit, cutting all entanglement would make the bulk space fall to pieces, leaving only disconnected fragments. In this view, the glue that holds space together is not a pre-existing geometric fabric, but the network of informational ties among deeper degrees of freedom. Space emerges as a kind of collective illusion sustained by entanglement. The philosophical ramifications are staggering. What does it mean to say that something is located somewhere if location is just a way of describing relations among bits of information? If all the data of our cosmic history can be stored on a distant horizon, what does it mean to say we inhabit the interior at all? Consider again the black hole, nature's most extreme laboratory of holography. When matter falls in, all the information that characterizes it, its pattern of fields, its quantum details, seems to become encoded on the event horizon's surface. From the outside, everything about the interior can, in principle, be read off that shimmering, light-trapping boundary. The interior's very existence becomes ambiguous. Perhaps it is simply the projection of data inscribed on the horizon. This insight leads to the famous black hole information paradox. If a black hole eventually evaporates via Hawking radiation, what happens to the information it contained? Does it vanish, violating the quantum rule that information is never destroyed? Or does it somehow leak back out in the radiation in ways we do not yet understand? The paradox remains a focal point for research and a clue to the nature of space-time itself. Here lies another cliffhanger. The resolution of the black hole information problem may reveal, once and for all, whether space is fundamental or merely emergent from deeper informational laws. For now, holography remains a framework, not a full theory of our cosmos, but its hints are compelling. It explains why gravity behaves as if it were weaker than other forces. It may be a large-scale, residual effect of micro-level degrees of freedom. It dovetails with the area scaling of black hole entropy, and it fits with the growing evidence that entanglement is key to building space-time. It also forces us to confront strange questions. If the universe is holographic, is there an edge we could reach? A literal surface where the encoding resides? In practice, no. The boundary may be at a kind of infinite distance, or on a cosmic horizon that forever recedes as we approach it. But conceptually, the idea teases the imagination. We might all be patterns written on a distant screen. Pause and reflect on the intimacy of this suggestion. Everything we hold dear, a loved one's face, the colors of a sunset, the vast gulfs between galaxies, may be emergent patterns in a more fundamental tapestry of information. The notion of here and there would be like the illusion of depth in a hologram, compelling to our senses, yet ultimately reducible to relations in a more basic, lower-dimensional code. Some physicists even speculate that the entire history of the universe might be describable by a kind of boundary computation, a cosmic program that generates the space-time we experience as it runs. If so, the expansion of the universe might be understood as the unfolding of more and more holographic data, the progressive realization of a grand informational script. This picture reshapes our intuitions about cosmology's ultimate questions. When we ask where the universe came from, we usually imagine a first instant of time and a first place in space. But if space itself is emergent, then the origin story may have to be told in terms of information coming into being, correlations being set, rules being encoded, a story less about location and more about logic. It also reframes the age-old philosophical query about what is real. In a holographic cosmos, our experience is no less genuine for being emergent. The holographic image in a lab can be beautiful, tangible to the eye, though it derives from a pattern in a flat plate. Likewise, the world we inhabit could be authentically rich and vivid, even if its depth is a secondary quality. Yet, the possibility unsettles us. We have always pictured the universe as a vast expanse. To be told that the expanse itself is an appearance forces us to rethink what we mean by existence. The word somewhere becomes slippery if space itself is derivative. The holographic principle thus does more than refine physics. It stirs metaphysics. It suggests that the quest to understand the universe is also a quest to understand how information begets reality, how relations give rise to the sense of place. As we look outward at the cosmos, we may, in a profound sense, be looking inward at the deeper logic that generates our perceptions. The great cosmic screen on which galaxies appear may be no more than the outward expression of an invisible ledger of information. In the end, the holographic universe is not a claim that we live in an illusion in the trivial sense. Not that the world is fake or imaginary. It is a claim that what we take as basic, the continuum of space, the separations between things, may be emergent features of a deeper level of description. This level is still mysterious. We do not yet know its language in full. Carry faith, whether it is best expressed in quantum field theories, in networks of entanglement, in some yet-to-be-discovered code. We only know that hints from black holes and from theoretical dualities point in this direction, and so we end this chapter with another tantalizing paradox. The more we explore the vast expanse around us, the more evidence we find that the expanse itself may be a grand projection. The ultimate map of the universe may not be spread across infinite space, but inscribed on a distant boundary. We are left to wonder, if the cosmos is a hologram, what lies beyond the screen? And is that even a meaningful question? Close your eyes for a moment and listen to a clock. Tick, tock, tick. We feel its beat as the sound of reality moving forward. The cadence of our lives slipping into the past. We tell ourselves that time flows like a river, sweeping us from birth to death. But what if that sensation is only a story our minds tell? What if there is no river at all? This idea may seem absurd at first. Every heartbeat, every falling leaf, every sunrise seems to confirm that time moves. Yet the more deeply we study the universe, the more that common-sense intuition begins to crumble. Einstein's relativity delivered the first great shock. In his vision, there is no single universal now. Events that seem simultaneous to you may not be simultaneous to someone racing past you at near the speed of light. Past, present, and future are not carved by a cosmic metronome, but depend on how each observer moves. The universe is better described as a four-dimensional space-time, a vast block in which all events, past and future, coexist as points in a single geometric structure. In this block universe, there is no objective flow from one moment to the next. All moments simply are. Our experience of a moving present is like the beam of a flashlight scanning across a painting. The picture is already there in its entirety, but we only illuminate one patch at a time. This notion unsettled even Einstein. He wrote to a friend mourning the loss of a loved one that, for us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. If time is just another dimension of the universe's fabric, like length or width, then change itself becomes a kind of perspective, a way of moving through the static block. Yet the world we perceive plainly has an arrow. We remember the past, but not the future. We grow older, never younger. Stars burn their fuel and fade. Glasses shatter but do not reassemble themselves. Where does that arrow come from? Here enters the second great insight. Entropy, the measure of disorder. In the 19th century, Ludwig Boltzmann and others showed that systems naturally evolve from less probable, more ordered states toward more probable, disordered states. A cup of hot tea cools because there are far more ways for its energy to disperse than for it to stay concentrated. The growth of entropy defines the arrow of time. We call the direction toward increasing entropy forward. In Einstein's block universe, the laws of physics themselves do not pick out a direction. The fundamental equations, whether of Newtonian mechanics, relativity, or quantum theory, work just as well if you run them backward as forward. It is the special, improbably low-entropy state of the early universe that gives time a direction. The Big Bang, for reasons still mysterious, began in extraordinary order. Ever since, the universe has been running downhill toward greater disorder, and our minds, like all structures in that universe, have evolved to perceive that downhill march as the passage of time. This insight is as humbling as it is astonishing. The forward flow of time may be less about the cosmos itself than about the initial conditions from which it emerged. Without that early low-entropy state, there would be no meaningful distinction between past and future. Only an eternal, static block. Yet even entropy may not be the whole story. Some researchers suggest that time's arrow may emerge more fundamentally from quantum entanglement, from the way correlations spread and grow in quantum systems. As entanglement increases, information becomes more diffuse and less recoverable, giving rise to the familiar sense of irreversibility. In this view, the arrow of time reflects the deepening interdependence of parts of the universe. Either way, the flow of time seems to arise, not from the basic equations, but from the structure and history of the universe. The ticking clock on the wall is not a cosmic engine driving change, but a local tool we devised to count processes in an evolving world. The change comes first. Our idea of a uniform flow of seconds is an abstraction. Pause and imagine what this means. If past, present, and future coexist in the block universe, then the moment you are experiencing right now is no more or less real than the moment of your birth or your distant death. See-do. Difference lies not in existence, but in your vantage point, in where your consciousness is situated in the four-dimensional structure. This realization carries both comfort and unease. Comfort, in that the moments we cherish are never truly gone. They are part of the eternal tapestry. Unease, in that the freedom we feel in moving forward may be an illusion. Our choices already inscribed in the structure of space-time. Philosophers have long wrestled with this tension. Presentism, the view that only the present is real, accords with our intuition but clashes with relativity. Eternalism, the view that all times are equally real, fits modern physics but challenges our sense of becoming. Perhaps both intuitions are partial truths, pointing toward a deeper understanding in which what we call time is a derived concept. Some physicists go further, suggesting that time is not even a basic dimension of the universe, but an emergent phenomenon. Like temperature, a single molecule has no temperature. Only a collection of many molecules with their jostling motions exhibits the property we call warmth. Similarly, perhaps the fundamental rules of physics know nothing of time. Only in large, coarse-grained descriptions do we perceive something that looks like a flowing continuum. In certain approaches to quantum gravity, time disappears entirely from the fundamental equations. The Wheeler-DeWitt equation, a candidate for describing the quantum state of the universe, is timeless. Change appears only when we divide the universe into subsystems and compare their states. Time may thus be an emergent bookkeeping of change, not a flowing backdrop. This perspective transforms our most intimate experiences. Memory, anticipation, loss. If the future already exists in the block, and the arrow we feel is just entropy's story, then memory is not a window into a vanished past, but a structural feature of our present state. We do not reach back. We stand in one slice of the block whose internal pattern includes records of other slices. Likewise, anticipation is not a glimpse into something unreal, but a projection encoded in our current neural patterns. Death, too, takes on a new complexion in such a cosmos. The moment of a person's life is not erased. It persists as part of the space-time tapestry. What passes is the continuation of experience, the shifting spotlight of awareness along the block's dimension. This does not diminish the poignancy of loss, but reframes it. All moments endure, but our consciousness does not traverse them freely. The mind rebels at this. We feel the world streaming past us, not ourselves moving through a frozen structure. Our emotions rise and fall with the sense of time's current, but perhaps that feeling is akin to the way we perceive motion in a movie, a succession of still frames shown rapidly enough to create the illusion of flow. The metaphor of a river may thus be misleading. Titritun. Better metaphor may be a vast crystalline lattice, each point a moment of the universe, all coexisting. What we call flow is our subjective journey through the lattice's structure, our brain's effort to stitch the world into a narrative. Scientific insight meets philosophical wonder here. If time is emergent, so too may be causality, the idea that one event produces another. Causality depends on the distinction between before and after. If that distinction arises only in certain regimes, then cause and effect may be large-scale approximations, not ultimate features of reality. This is perhaps the deepest paradox. We build our understanding of the world on the bedrock of causes and consequences. Yet that bedrock may itself be a construction of higher-level patterns. At the most fundamental layer, reality may be less like a chain of events and more like a timeless web of relationships. Some approaches to quantum cosmology embrace this idea explicitly. The universe, in such models, is described by a timeless wave function. What we perceive as dynamics, the evolution of galaxies, the unfolding of our own lives, is a kind of internal bookkeeping, a pattern arising from comparing one part of the wave function to another. Pause to consider what that means for the Big Bang. We often speak of it as the beginning of time, but if time is emergent, then the Big Bang might be not a starting point, but a boundary condition, the special low-entropy state from which the arrow of time arises. The implication is humbling. The question, what happened before the Big Bang, may be meaningless if before presupposes a temporal framework that did not yet exist. The universe's origin may be more like the emergence of space and time from a deeper, non-temporal order than like an event within time. Our emotional lives are tied to time's apparent passage. We celebrate birthdays, mourn endings, plan futures. The physics that dissolves that passage does not dissolve those emotions, but it does invite us to see them differently, as responses to change within our perspective, not as evidence of an external river. Entropy remains the practical guide to our arrow. Stars burn their fuel, galaxies thin their gas. The cosmos itself stretches into ever greater uniformity. Against this vast drift toward disorder, Life's brief ordered structures arise and fall like intricate eddies in a stream. Our sense of history, progress, and loss are the local testimonies of that cosmic gradient. But the recognition that the gradient, and thus the arrow, arise from boundary conditions rather than fundamental laws shifts the focus. It tells us that the forward rush we feel is not woven into the deepest code of reality. Change is real, but the stage on which we measure it may be a mirage. This realization, unsettling as it is, opens new paths for thought. It invites us to look for principles deeper than space-time, to search for the mechanisms by which order and correlation emerge, and to recognize that our common-sense picture of a flowing present may be a practical fiction. In the end, the illusion of time does not make the universe any less wondrous. If anything, it reveals a richer depth beneath appearances, a cosmos whose fundamental nature may be timeless, yet capable of giving rise to histories and memories, to beginnings and endings. We began this chapter with the tick of a clock, a symbol of time's supposed flow. We close with a different image, a vast frozen wave, its crests and troughs stretching across space-time, each point a moment, all equally real. Our lives trace a path across that pattern, but the river itself does not run, and if time is emergent, then perhaps even causality, the thread that ties one moment to the next, is a story told by the structure we inhabit, not a law of the ultimate realm. To grasp this is to stand on the edge of a profound new understanding, that the universe's most intimate dimension may be a grand illusion, and that what we call the passage of time may be only the way our minds mark the changing relationships in an underlying timeless whole. When you open your eyes in the morning, the world seems to be waiting out there. The walls of the room, the clock on the nightstand, the slow drift of sunlight across the floor. It feels as if you are simply receiving reality, as if space and time are there first, and your mind merely looks on. But what if that sense is backward? What if the world as you perceive it is not the objective foundation of existence, but a map your mind has drawn, a map optimized for survival, not for truth? This idea is as unsettling as it is fascinating. For centuries, science has taught us to doubt appearances. The earth feels stationary but spins. The ground seems flat but curves. Colors seem intrinsic to objects but are the mind's translation of wavelengths. Now, some researchers suggest that our most basic experiences of space, of time, of a solid world unfolding around us, may likewise be part of a useful interface, not a window into things as they really are. Evolutionary biologist Donald Hoffman has argued that organisms do not evolve to perceive objective reality. They evolve to perceive what helps them survive. A desktop computer icon tells you nothing of the transistors beneath it. It is useful precisely because it hides the underlying complexity and presents only what you need to act. In the same way, the colors, shapes, distances, even the sense of before and after that we perceive may be the icons of an adaptive interface. We navigate by these icons as we navigate by the icons on a screen, never seeing the raw circuitry. If that is so, then our senses, and by extension, our science, begin not with reality as it is, but with a coded translation shaped by natural selection. Space may be the mind's way of arranging experiences, time the mind's way of ordering them. The very fabric that physics measures may be the user interface of a deeply hidden operating system. Pause to consider the paradox this raises. If space and time themselves arise from how we perceive, then what does it mean to speak of a cosmos that existed before perceivers evolved? What is a location or a moment in a world where those notions are not yet defined? Most physicists remain cautious about such speculations. They look for objective structures, quantum fields, geometric relations, entanglement patterns that give rise to space-time. But even among them, a quiet awareness persists. Any description of the universe is framed in terms that we, as observers, can understand and record. Our theories use mathematical models, but their meaning is tied to observations made by conscious beings. This boundary between physics and the mind is becoming less easy to ignore. In quantum mechanics, the act of measurement plays a central role. A system can exist in a superposition of states, many possibilities, at once, until it is observed or interacts with an environment in a way that records an outcome. Some interpretations suggest that the boundary between possible and actual is drawn by the process of observation itself. That does not mean the universe pops into being because we look at it. Such solipsism would be absurd, but it does mean that the notions of event and record, of something happening at a specific place and time, are inseparable from the structure of interaction and information exchange. Conscious observers are part of that. Their presence shapes the questions that can even be meaningfully asked. Cognitive science strengthens this perspective. Neuroscience shows that what we experience is not a direct imprint of the world, but a construction generated by the brain. The sense of a stable visual scene is assembled from saccadic snapshots. The sense of hearing is stitched together from vibrations, filtered and interpreted. Even the sense of a continuous self moving through time is a narrative woven by neural networks from moment to moment. In the laboratory, researchers have demonstrated how easily our perception of time can be stretched, compressed, or inverted by context and expectation. In certain approaches to quantum gravity, time disappears entirely from the fundamental equations. The Wheeler-DeWitt equation, a candidate for describing the quantum state of the universe, is timeless. Change appears only when we divide the universe into subsystems and compare their states. Time may thus be an emergent bookkeeping of change, not a flowing backdrop. This perspective transforms our most intimate experiences: memory, anticipation, loss. If the future already exists in the block, and the arrow we feel is just entropy's story, then memory is not a window into a vanished past, but a structural feature of our present state. We do not reach back. We stand in one slice of the block whose internal pattern includes records of other slices. Likewise, anticipation is not a glimpse into something unreal, but a projection encoded in our current neural patterns. Death, too, takes on a new complexion in such a cosmos. The moment of a person's life is not erased. It persists as part of the space-time tapestry. What passes is the continuation of experience, the shifting spotlight of awareness along the block's dimension. This does not diminish the poignancy of loss, but reframes it. All moments endure, but our consciousness does not traverse them freely. The mind rebels at this. We feel the world streaming past us, not ourselves moving through a frozen structure. Our emotions rise and fall with the sense of time's current, but perhaps that feeling is akin to the way we perceive motion in a movie, a succession of still frames shown rapidly enough to create the illusion of flow. The metaphor of a river may thus be misleading. Surety, better metaphor may be a vast crystalline lattice, each point a moment of the universe, all coexisting. What we call flow is our subjective journey through the lattice's structure, our brain's effort to stitch the world into a narrative. Scientific insight meets philosophical wonder here. If time is emergent, so too may be causality, the idea that one event produces another. Causality depends on the distinction between before and after. If that distinction arises only in certain regimes, then cause and effect may be large-scale approximations, not ultimate features of reality. This is perhaps the deepest paradox. We build our understanding of the world on the bedrock of causes and consequences, yet that bedrock may itself be a construction of higher-level patterns. At the most fundamental layer, reality may be less like a chain of events and more like a timeless web of relationships. Some approaches to quantum cosmology embrace this idea explicitly. The universe, in such models, is described by a timeless wave function. What we perceive as dynamics, the evolution of galaxies, the unfolding of our own lives, is a kind of internal bookkeeping, a pattern arising from comparing one part of the wave function to another. Pause to consider what that means for the Big Bang. We often speak of it as the beginning of time, but if time is emergent, then the Big Bang might be not a starting point, but a boundary condition, the special low-entropy state from which the arrow of time arises. The implication is humbling. The question, what happened before the Big Bang, may be meaningless if before presupposes a temporal framework that did not yet exist. The universe's origin may be more like the emergence of space and time from a deeper, non-temporal order than like an event within time. Our emotional lives are tied to time's apparent passage. We celebrate birthdays, mourn endings, plan futures. The physics that dissolves that passage does not dissolve those emotions, but it does invite us to see them differently, as responses to change within our perspective, not as evidence of an external river. Entropy remains the practical guide to our arrow. Stars burn their fuel, galaxies thin their gas. The cosmos itself stretches into ever greater uniformity. Against this vast drift toward disorder, life's brief ordered structures arise and fall like intricate eddies in a stream. Our sense of history, progress, and loss are the local testimonies of that cosmic gradient. But the recognition that the gradient, and thus the arrow, arise from boundary conditions rather than fundamental laws shifts the focus. It tells us that the forward rush we feel is not woven into the deepest code of reality. Change is real, but the stage on which we measure it may be a mirage. This realization, unsettling as it is, opens new paths for thought. It invites us to look for principles deeper than space-time, to search for the mechanisms by which order and correlation emerge, and to recognize that our common-sense picture of a flowing present may be a practical fiction. In the end, the illusion of time does not make the universe any less wondrous. If anything, it reveals a richer depth beneath appearances, a cosmos whose fundamental nature may be timeless, yet capable of giving rise to histories and memories, to beginnings and endings. We began this chapter with the tick of a clock, a symbol of time's supposed flow. We close with a different image, a vast frozen wave, its crests and troughs stretching across space-time, each point a moment, all equally real. Our lives trace a path across that pattern, but the river itself does not run. And if time is emergent, then perhaps even causality, the thread that ties one moment to the next, is a story told by the structure we inhabit, not a law of the ultimate realm. To grasp this is to stand on the edge of a profound new understanding, that the universe's most intimate dimension may be a grand illusion, and that what we call the passage of time may be only the way our minds mark the changing relationships in an underlying timeless whole. When you open your eyes in the morning, the world seems to be waiting out there. The walls of the room, the clock on the nightstand, the slow drift of sunlight across the floor. It feels as if you are simply receiving reality, as if space and time are there first, and your mind merely looks on. But what if that sense is backward? What if the world as you perceive it is not the objective foundation of existence, but a map your mind has drawn? A map optimized for survival, not for truth. This idea is as unsettling as it is fascinating. For centuries, science has taught us to doubt appearances. The earth feels stationary but spins. The ground seems flat but curves. Colors seem intrinsic to objects, but are the mind's translation of wavelengths. Now, some researchers suggest that our most basic experiences of space, of time, of a solid world unfolding around us, may likewise be part of a useful interface, not a window into things as they really are. Evolutionary biologist Donald Hoffman has argued that organisms do not evolve to perceive objective reality. They evolve to perceive what helps them survive. A desktop computer icon tells you nothing of the transistors beneath it. It is useful precisely because it hides the underlying complexity and presents only what you need to act. In the same way, the colors, shapes, distances, even the sense of before and after that we perceive may be the icons of an adaptive interface. We navigate by these icons as we navigate by the icons on a screen, never seeing the raw circuitry. If that is so, then our senses, and by extension, our science, begin not with reality as it is, but with a coded translation shaped by natural selection. Space may be the mind's way of arranging experiences, time the mind's way of ordering them. The very fabric that physics measures may be the user interface of a deeply hidden operating system. Pause to consider the paradox this raises. If space and time themselves arise from how we perceive, then what does it mean to speak of a cosmos that existed before perceivers evolved? What is a location or a moment in a world where those notions are not yet defined? Most physicists remain cautious about such speculations. They look for objective structures, quantum fields, geometric relations, entanglement patterns that give rise to space-time. But even among them, a quiet awareness persists. Any description of the universe is framed in terms that we, as observers, can understand and record. Our theories use mathematical models, but their meaning is tied to observations made by conscious beings. This boundary between physics and the mind is becoming less easy to ignore. In quantum mechanics, the act of measurement plays a central role. A system can exist in a superposition of states, many possibilities, at once, until it is observed or interacts with an environment in a way that records an outcome. Some interpretations suggest that the boundary between possible and actual is drawn by the process of observation itself. That does not mean the universe pops into being because we look at it. Such solipsism would be absurd, but it does mean that the notions of event and record, of something happening at a specific place and time, are inseparable from the structure of interaction and information exchange. Conscious observers are part of that. Without their presence shapes the questions that can even be meaningfully asked. Cognitive science strengthens this perspective. Neuroscience shows that what we experience is not a direct imprint of the world, but a construction generated by the brain. The sense of a stable visual scene is assembled from saccadic snapshots. The sense of hearing is stitched together from vibrations, filtered and interpreted. Even the sense of a continuous self moving through time is a narrative woven by neural networks from moment to moment. In the laboratory, researchers have demonstrated how easily our perception of time can be stretched, compressed, or inverted by context and expectation. The mystery, however, is not a wall blocking us. It is an invitation. The illusions of space and time, far from being deceptions, may be bridges, patterns that translate the deeper reality into something that conscious beings can navigate and explore. We may never see that deeper level directly, but the illusions themselves can guide us toward it, the way ripples on the surface of a lake hint at the depths below. Pause for a moment and imagine the universe as a vast tapestry. For centuries we thought the tapestry itself was the ultimate thing. Then we realized it might be woven from threads, space-time, particles, fields. Now we suspect the threads themselves are patterns of information, perhaps even patterns that depend on the observer. Yet when we step back, the image the tapestry forms is no less real, no less beautiful. The illusion is not a lie. It is the visible face of something deeper. In this light, the boundary between science and philosophy softens. The quest for a theory of everything becomes inseparable from the quest to understand meaning. If the universe at its core is a network of relations, or a vast quantum state, or something stranger still, then what we call space and time are its language, not its substance. To know the truth may be less like finding the last brick in a wall, and more like learning a new way to read. This recognition humbles us, but also unites us. No one human perspective, no one era of science can claim to have the final word. We are a species only beginning to glimpse that the stage we walk upon is itself part of the play. The very urge to explore, to measure, to think, to wonder, is itself a phenomenon arising within the illusion, and yet that urge may be the clearest sign that the illusion is a bridge. It carries minds like ours across the gulf between appearance and reality. There is awe in this thought. The illusions we inherit from physics and from perception may not be errors to be discarded, but the first level of a grand Translation: a child's drawing of the sky is not the sky, yet it opens the way to understanding. So too are concepts of space and time, however provisional, may be stepping stones toward an ever deeper grasp of the source. Picture a cosmic tapestry slowly folding back, revealing behind its woven galaxies and curving horizons a glow without form or boundary, a light not in space, not in time, but giving rise to both. That image is only a metaphor, yet it captures a truth. The depth beyond the illusion may be not a darker void, but a greater light, hidden from us only by the limits of our current vision. Some might hear in these thoughts an echo of ancient mysticism, the idea that the world is Maya, appearance, not ultimate reality. Modern science does not endorse such metaphysics, yet it cannot deny the resonance. What physics now glimpses through black holes and quantum fields is that the reality we navigate is indeed layered, and that the layers accessible to us may be only a small part of the whole. There is also hope in this recognition. It suggests that the mystery is not a fortress designed to keep us out, but a frontier, inviting us forward. We do not need to despair at our ignorance. We can marvel at the fact that we can even ask these questions, that from within the illusion, we can point toward what lies beyond it. Pause again for reflection. When you look up at the night sky and see 1,000 stars, you may be seeing not just distant suns, but patterns on a screen, shadows of a deeper order. And yet, does that make them less wondrous? Or does it reveal that wonder itself is part of the deeper order? That the capacity to feel awe is one of the ways the hidden truth discloses itself? In this closing vision, the separation between the observer and the observed begins to blur. We do not stand outside the cosmos, peering in. We are participants in its unfolding, expressions of the same underlying depth that gives rise to space and time. To seek the foundation of the universe is also to seek the foundation of ourselves. Perhaps this is the final paradox. The illusion may not veil the truth but reveal it in a form we can apprehend. The untwight, visible river of time may be the shimmer of an unseen current. The vast expanse of space may be the shape taken by relations that cannot be pictured. The quest for a deeper reality may lead us not to discard the world we know, but to see it as the first translation of something that transcends translation as our theories advance, as quantum gravity slowly takes shape, as we probe the cosmic dawn and decode the relic ripples of space-time. We may not find a single answer, but an ever-expanding horizon. And perhaps that is fitting. A final, closed theory might satisfy the intellect, but would leave no room for wonder. An open horizon keeps wonder alive, keeps us reaching. Imagine, in the final image, an observer standing at the edge of a dark ocean, gazing out as the stars dissolve into a luminous mist. The figure's silhouette wavers, then fades, becoming indistinguishable from the light. In that moment, the distinction between subject and object, between the seeker and the sought, dissolves. What remains is curiosity itself, the spark that asks and listens, we cannot yet say. What lies beneath space and time, we can say only that the journey to find out has already transformed our vision. It has shown us that the most familiar aspects of reality, distance, duration, direction, may be emergent. It has revealed that the boundary between physics and philosophy, between measurement and meaning, is porous, and it has taught us that mystery is not an obstacle to understanding, but part of what makes understanding worth pursuing. The illusion of space and time, far from being a cosmic trick, may be the bridge to truth, the interface through which a deeper order becomes visible. To stand on that bridge is to live in wonder, to accept that the universe may be both more knowable and more mysterious than we can yet imagine. As we close this exploration, let the final thought be not an answer, but an invitation. The next insight may come from equations written on a physicist's board, or from a new telescope's glimpse of the early cosmos, or from a philosopher's meditation on the nature of experience. Wherever it comes from, it will remind us again that the story is not finished. The cosmic tapestry continues to unfold. Its patterns of space and time shimmer like mirages on a deeper sea. We, conscious beings who ask, who wonder, are part of that unfolding. And the horizon ahead, expanding into darkness, is not the edge of knowledge, but the promise of discovery.